Okay, so current is defined as the amount of charge passing a point, or one way to think of it anyway, is the amount of charge passing a point in a given time. So if 12 coulombs of charge passes by in 4 seconds, right, then you might have a current of 3 coulombs per second. Okay, this is all pretty basic stuff. So it's like it's like we're talking about water going by in a pipe. If it's 5 gallons per minute, then that might be the flow rate, right? So this is an analogy that we'll use is water flowing in a pipe or something like that, right? Okay. And there's some places where the analogy breaks down, but generally it's a pretty good analogy. But at this point, let me just remind you, well, I'm not going to remind you, I'm just going to tell you that it's not true that a coulomb, that an ampere is defined as a coulomb per second, okay? It is true that a coulomb, if a coulomb per second is flowing by on 2 straight wires, exactly a meter apart, if you have 2 long straight wires, they generate a magnetic field, and an ampere is defined in this way, right? An ampere is the amount of current flowing in each of 2 long straight parallel wires such that there is a force of 2 times 10 to the minus 7th, exactly, 2 times 10 to the minus 7th newtons per meter of length. That's a mouthful, isn't it? Right? So we don't understand magnetic field yet, okay, much less, 2 wires and all this stuff, right? So let's just say that the ampere is defined in terms of force and length and time, okay, in using last year's units. And in fact, a coulomb is actually defined as the amount of charge that will have gone by if an ampere is flowing for 1 second, or 2 amperes for half a second or something like that, right? Okay, so our example question is, what charge passes a certain point if a current of 250 milliamps flows for 12 minutes. So this is as hard as one of these problems could be, right? So we're solving for Q, right? And if we solve that for Q, and you're looking for the formula for Q, right? Isn't that what you're looking for? Yeah. Right? And you solve it, you would say that, well, that's it. Okay, sorry. Okay. That's okay. So the milliamps, 250 milliamps is equal to 250 times 10 to the minus 3rd amps, and it's also 0.250 amps, like that, right? And so we can go 0.250 amps, and then 12 minutes times 60 seconds per minute. My God, this is so hard, right? Okay. Well, 12 times 60 is it 720 seconds? Okay. And an ampere could be thought of as a coulomb per second, and so this times this, what's a quarter of 720? Well, that would be, is that 180? Yeah. Half would be 360, half of that would be 180. Yeah, so isn't this a lot of coulombs? Okay, 12 minutes is not much time. A quarter of an amp is not that much current. I could get a tiny wire to carry that much current. 180 coulombs is just a buttload of charge, isn't it? That's like amazing. And so in the last chapter we learned that the coulombs were like, a coulomb was, if we had a coulomb of charge, or 4 coulombs of charge, I think we had to go all the way to the coast. We had 3 coulombs and 4, or some problem like that, right? We could go like 100 miles away and it still exerted a force of a pound, right? Okay, so the question here is you're going, gee, that's 180 coulombs. How could that possibly happen in some electric wire in a flashlight or something like that, right? And the answer is that electric charge is just electrons moving down a wire. So a wire is like all these nuclei, right? And the electrons are just moving down the wire, and the electrons are very, very close to those protons that are in the nucleus. They are still very, very close. They're 10 to the minus 10th meters away or something like that. They're very, very close. And so at a distance, the net charge is still pretty much 0 on that wire, yes? Even if there's a coulomb flowing by per second, at any given instant, you've got about the right number of electrons on that wire with all the protons, yes? So the wire is pretty much neutrally charged, right? I'm saying pretty much because there has to exist some electric field to make the charge move down the wire. So it's the difference between Let's take the electrons off the wire and put them far away. That would be a tremendous amount of potential energy. That would cause an explosion, right? And let's shuffle the electrons along the wire very close to the nucleus. Yeah? Does that make sense? So an electric current, that's what's going on, is that the electrons are on the wire, they're shuffling along. This is why, and this is the big difference between water in a pipe and the wire. If I cut the wire, the electrons just simply stop flowing. They don't like flow off into the room, because to do so it would take a lot of energy to do that, right? We've calculated that. That's like last chapter, right? To make them flow away from the wire is very hard. They want to stay on the wire. So if I cut the wire, they just go, and they don't go any farther, okay? If I cut a pipe, of course, the water just goes all over, right? My uncle did that one time by accident, drilling a hole. Yeah, he drilled a hole in a shower wall to put up like a handle to hold on to, right? Only he drilled it right through a pipe. It was the hot water pipe, which was good. No, that was a good thing, because a hot water pipe goes through the water heater, and all water heaters have a thing to. Is this for Laurel? She's not here. Yeah. Hot water heaters all have a valve to shut off the hot water heater, to switch out the hot water heater. Otherwise, if you live in an apartment, you don't have a cold water shutoff in your apartment, because normally people don't drill holes in pipes. Yeah. So he shut it off, and then he actually made, he's retired, he's an engineer, he made an epoxy thing that glued over the pipe and fixed it. I know. Okay. So really a coulomb is actually defined as an amp second. Try that. Here's a whiteboard problem. That's a whiteboard, baby. And hurry up. We got a lot to do today. Whiteboards, there's whiteboards up here. Pass them around. There's a big pile here. Can you guys pass those around that are... Just pass like a whole stack backwards.
I gave it back. You did not give it back to me, Jackie. I definitely gave it back to you.